Atmospheric pressure. Here's a philosophical question. Do fish know that they are living in a fluid? Do you? Well, whether you do or not, you do live in a fluid. The atmosphere we live in is a pretty dense fluid. Not as dense as water or rock, but a lot denser than most of the universe. We live in this fluid all our lives, so we don't think about it. But we are always moving through it, and it is always pressing on us. Here's a great video of a demonstration that can be done to show that air behaves like a fluid. The thin band of blue, right there, and this arrow is pointing to it also. It's very thin, okay? That's the thin layer of atmosphere or fluid that surrounds and protects Earth. Here, we've expanded the relative size of the atmosphere for clarity. The previous slide showed you just how thin it is, but here we're making it a little bigger so we could fit those arrows in and write atmosphere. Earth's atmosphere has mass, and it's attracted to Earth's center like any other mass near Earth. It pushes down, creating a pressure on everything on the surface of the Earth. That pressure is the same as that due to any fluid, density times G times H. The mass of air pushing down on every square meter of the surface of the Earth is more than 10,000 kilograms. That's a lot. The weight of that air is about 101,000 newtons per square meter. So the resulting pressure is the force divided by the area, or 101,000 newtons per square meter. So here's your square meter here on the Earth. Here's the square meter up to the top of the atmosphere. Okay, then outside here is space. And then the value of this entire mass here, that's the 10,000 kilograms, and the pressure on the surface of the Earth is 101,000 newtons per square meter, and that's also called 1 atmosphere. Your head and shoulders, as viewed from above, have an area about 0.1 square meters. So a force of 101,000 newtons due to the mass of air is pushing down on you. That's equivalent to 1 ton of weight in non-SI units, a small car. Now, if you tried to lift a small car, you'd certainly notice it, and you wouldn't be able to. So why don't we notice that there's a ton of air pressing down on us? Well, the air exerts this force in all directions, so as well as pushing down on us, it also pushes up and balances out the force on our bodies so that we don't collapse. The force acting downwards on this small table, with the chess notation here, would be 300,000 newtons, about 66,000 pounds. Why doesn't the table collapse? Think back on that cube that we put in water before. Not only did you have a force there, you had forces on all sides, okay? Gases exert their pressure in all directions, as do all fluids. The force of air pushing down is opposed by an equal force pushing up. If you were to take the air away below the table, it would collapse. When we drink through a straw, we are reducing the atmospheric pressure on one side of the straw. That would be the piece in your mouth there. The air above the soda keeps the pressure high, that's the atmospheric pressure, so fluid rushes to the low pressure area, like that, and up the straw. The low pressure in your mouth results in the liquid moving up the straw. We breathe by the diaphragm muscle in the chest. Here's the muscle here. It flattens out, which increases the volume of the lungs. Okay, the diaphragm was going down this way. When the volume increases, the pressure decreases. The higher atmospheric pressure enables air to flow into the lungs as a fluid. Air in this case flows from high to low pressure. That's called inhaling. The diaphragm then moves up, that's in this direction right here, that decreases the lung volume and increases its pressure above atmospheric pressure. A fluid flows from high to low pressure, so the air moves out. That's exhaling. A straw is filled with liquid by lowering it into a glass. And what happens then is the fluid rushes up into the straw, okay? The top of the straw is then covered with a finger so that air pressure cannot push down on the liquid. What happens when the straw is pulled out of the liquid, keeping the top covered? The air pressure pushes up from the bottom, right? If I've got the straw out of the glass, the air pressure now pushes up so the fluid cannot come out. If the top is uncovered then, right, pull the finger away, the pressure on the top and bottom of the straw is the same now. The net force acting on the fluid is due only to gravity, okay, not due to the air pressure on the top or the bottom of the straw, and the fluid falls out of the straw due to gravity. A glass can be filled with water with only the unattached paper beneath it keeping the water in. Once again, we have air pressure pushing up on the water in the glass and the paper below it through the open end of the glass. The closed end of the glass up here blocks air from pushing down on the water. That provides a net upward force on the water and keeps it in the glass. The barometer is a device for measuring atmospheric pressure. A tube filled with liquid, here's your tube filled with liquid, is turned upside down in a container of the same liquid. So in this case, you have liquid mercury, and no, they don't make barometers or thermometers with mercury anymore because it's somewhat of a hazardous chemical. But in this case, we have this mercury. It's turned upside down in a container of the same liquid, more mercury. The atmosphere pushes down on the surface of the liquid in the container. The liquid falls in the tube until the pressure from this column of liquid equals the pressure of the atmosphere on the surface of the liquid in the container. The height of fluid in the tube is then a measure of atmospheric pressure. The atmosphere pushes down on the liquid surface. So why does that push up on the liquid in the tube? We learned earlier that pressure in a fluid is the same everywhere within the fluid that is at the same depth. That's key right there. And that pressure acts in a direction that is perpendicular to the fluid surface. In this case, the pressure of the column of air pressing down on the surface of mercury results in an equal pressure from the mercury pushing up from the surface to the bottom of the tube. Any substance could be used to build a barometer, but the greater the density of the liquid, the smaller the height required. So if you used water for some strange reason, okay, that has this density here, you would need a height of the column to be 30 foot to measure normal atmospheric pressures. If you use mercury, which has a higher density, you'd only have to go 2.5 feet. Normal atmospheric pressure at sea level is referred to as standard pressure. It is equal to all of these values. 1 atmosphere, which we hinted at earlier, 1.01 bar, 760 millimeters of mercury, that would be the height of the column of mercury in a barometer, 760 torr, or 101,000 newtons per square meter. Mercury Manometer. This device is used to measure the difference between atmospheric pressure and the pressure of a gas in a vessel. So here's our vessel, and we have gas exerting a pressure like that, goes through here, and in here we have some mercury, okay? And the other force acting is the pressure of the atmosphere on the open end. If the height of the mercury is higher in the open end of the tube, as we show here, then the gas pressure in the vessel is greater than atmospheric pressure because it's pushing it down farther than the atmospheric pressure is trying to push it. Now let's take the other case and let's erase this here. And what if we had the level of the mercury was up here on that side and it was only here, okay? That means the gas pressure in the vessel is less than atmospheric pressure.